So let's start with the elementary sorting algorithms. Before we begin, quickly, all of these, their runtimes are O of n squared. Okay, O of n squared. So you'll notice this is one of the slowest algorithms that we will see in this course so far. Okay, O of n squared, we've said this thing in the beginning when we were talking about runtime analysis, that quadratic is not a very good time. We'll try to avoid it. If I show you a code, okay, you can just look at the code and say the runtime based on the positioning or the number of loops in the code. So for example, if you have a nested loop, okay, most likely its runtime is going to be O of n squared. So we'll see this now, that all of these three algorithms, bubble sort, selection sort, insertion sort, all of them are quadratic. And when you look at the code, you'll be able to see that because there is going to be a nested loop, two for loops nested together. So let's first have a look at bubble sort. Bubble sort is perhaps the worst sorting algorithm. You guys already studied this in CS101. So I'll show you an example first with a simple array. Okay, a very small array. So I'm going to put some values here. And I'd like to sort this in ascending order. Okay, so imagine this is my array called A, and these are my positions, 0, 1, 2, and 3. Okay, bubble sort goes like this. So imagine A is given to you already. Okay, and let's say an integer n equals to a dot length. Okay, so in this case, a dot length is 4, so n would be 4. So we'll go with integer I is 0, I is less than n, and I plus plus. So we're going to have a double loop, and then another loop. Sorry, we should go with j. Okay, so clearly these loops are not linked together. Both of them are running exactly n number of times. Okay, here we're going to have an if condition. So if a of I is less than a of j, if this is true, we're going to swap it. So to swap, we can use an integer temporary variable. We're going to copy a of I here. And then we say a of I equals a of j, and a of j equals temp. So this is the swap code, and we've seen it many, many times before. And there you go. This is your bubble sort method or bubble sort code. So you can put all this in a method, and it will work just fine. So let's try to trace this a little bit. Let's see how this is going to work out for us. So I'm going to try to trace it here. Okay, so when this loop starts, okay, I is here and j is here. Okay, these are the position for I and j. So in the beginning, I is 0, j is 0. So we get into the first loop, get into the second loop, and then we compare a of 0 with a of 0. Isn't this wasting of time? We're comparing the same value with itself. Yeah, so 1 is going to compare with 1, no need to swap. Okay, and then j plus plus, so it's going to become 0 and 1. Okay, so we compare this value with this value. So a of I is smaller than a of j, 1 is less than 4. True. So we'll go inside and we'll swap it. Okay, this time around we swap it. So this will become 4 and this will become 1. Okay, j plus plus. So again 0 and j becomes 2. So now we're going to compare the value at position 0, which is 4 now, with 3. So now we're saying, is 4 less than 3? No, so we do not swap it. Okay, and then j plus plus. So this will be 0, 3. Okay, now we compare 4 with 2. 4 is less than 2. No, it's not. Okay, so we do not swap. So this is our first iteration. The outer loop ran one time now. I will increment, so I becomes 1 and j becomes 0. Okay, so we repeat the whole process again. Okay, notice this ran 4 times. In other words, n times. Okay, let's go with the second iteration. So now I is 1 and j is 0. So we're comparing 1 is less than 4, true, so we'll swap it. Okay, we swap it. Now what happens is this becomes 1 again, and this becomes 4. So you can see this thing, there was unnecessary movement here. Okay, anyways, let's continue. So j plus plus, I is 1, j is 1. Of course, it's going to compare with itself, so it will not swap. And then 1 and 2. Okay, so I is 1 and j is 2. And we compare 4 with 3. Is 4 smaller than 3? It's not. So we do not swap. And then j plus plus, j becomes 3. So again, now we compare 4 with 2. 4 is less than 2. No, it's not. So we do not swap. Okay, so again, this is n operations. All right, again, we go back to the outer loop. So I plus plus, now I becomes 2. So we'll do the same thing again, compare 2 with 0, position 2 with position 0. So 3 is less than 1. No, it's not. Okay, then 2 and 1. So 3 compared with 4. Yes, it is. 3 is smaller than 4. This means now we have a swap. So this becomes 3 and this becomes 4 now. Okay, and then 2, 2, of course, nothing is going to happen. And then 2, 3. So we're going to compare a of I, we have 2, which is 4. 4 less than 2, no, it's not. So nothing happens. Okay, so again, this is n operations. Okay, and now the last iteration, I plus plus. So I becomes 3. Of course, 3 is less than 4, so we'll go with the third iteration. So 3 and 0. So we compare now 2 with 1. Is 2 smaller than 1? No, it's not. Okay, so nothing happens. 3, compare these two. 2 is smaller than 3. Yes. Okay, so we're going to move this or swap it. So this becomes 2. Okay, now 3 with 2. So 3 is smaller than 4. Yes. So it's going to swap it. This becomes 3. This becomes 4. Okay. And the last one, 3, 3. Nothing is going to happen. So now you can see this thing, our overall data is now sorted. We have 1 here, we have 2 here, 3 here, and 4 here. But at what cost? Okay, what's the total number of operations that we did? It's exactly n squared. Okay, so we can do 2 things. We can check the comparisons. Okay, how many comparisons did you make, which was n squared? And how many swaps did you make? Okay, so here we made 1 swap, 1 swap, 1 swap, and 2 swaps. So in total, we had 5 swaps. If I want to give a big O notation for this, okay, big O would be big O of n squared. Here, this is exactly O of n squared. This would be O of n squared. That's the worst case scenario. Right. What if the data is already sorted? What's going to happen? What if it was already 1 and 2 and 3 and 4? Anybody? How many comparisons would be needed?
O of n, Doctor.
Sure, O of n? Anybody else? Safin, Hamadi? Nobody? Okay. So yeah, if it is already sorted, okay, number of comparisons would still be exactly the same. Okay, it would still give you O of n squared, number of comparisons. But your swaps could change. Okay, maybe now you have to do less number of swaps. So it depends on experimental evaluation. It also depends on the positioning of the data. But now overall, for bubble sort, we can safely say that the runtime is O of n squared. Okay, so this is one of the worst sorting algorithms. Notice that we're wasting time. Why are we comparing positions which are similar? I mean, the same item compares to itself. We can skip this. If you do that, we can improve this algorithm. Okay, now let's go and have a look at the slides. I'm going to open these slides. Okay, so again, these slides are taken from the Algorithms book by Robert Sedgwick and Wayne. All right, so here are some basics for sorting. Usually we have some data that appears either as a table, a tuple, series, or something of this sort. So what you see in front of you is a two-dimensional array or a simple table. So we have rows and we have columns. Right. In sorting terms, a row is referred to as an item. And of course, a column is a column. Now, usually, there is one value which uniquely determines the item. Okay, so this value is called a key. In other words, key must be unique within its column. So what you see in front of you, for example, battle, okay, does not appear again in the same column, in the names column. But for the other columns, you can see the things could appear again. For example, the second column is for GPA. You can see 3 is appearing many times, 4 is appearing many times, and so on. The third column is grade. So same thing, it's not a key column, which means the value could repeat. Same goes with the fourth and the fifth column. So fourth column is the phone number. It is possible two people have the same phone number. And the address, okay? Both of them, they live at the same address. So the one column which uniquely defines all the items is called the key column. Okay, so if I say, please rearrange my table in ascending order, so we're going to sort it by the key column. Here, the key column is the name, so we're going to sort it by the names. Of course, A comes before B and C and D and so on. So now you can see this thing, Andrews appears on the top, next is Battle, then Chen, Furia, and so on. You can notice that all the entire row for Andrews moved up, okay? It's not like we only changed one value, which was the key. No, it's the entire item which gets sorted, or the entire row that gets sorted. Okay, some applications for sorting. So you're familiar with the Dewey numbers in the library. When you go to the library, okay, each book or each item or each title has a unique number. So, and they use certain kind of a code to describe where to find the book. And in the library, you have multiple floors. Each floor has multiple racks, or each rack you have multiple sets of titles or books. So using this coding scheme, you can easily go and find the item or the title that you're looking for. FedEx or DHL, okay, these packages are also sorted in a certain way. Each one of them is described by a unique code, and we use that code for sorting and shipping purposes. Playing cards are also sorted. Okay, so we have 4 houses. Each house has 13 cards. Contacts in your phone are also sorted. And of course, if you're a Harry Potter fan, Hogwarts houses are sorted by the hat. Okay, so Let's look at some simple definitions. The goal for sorting is that we should be able to sort any kind of data as long as it can be sorted. A total order is a binary relation, okay? It's a binary relation that satisfies these conditions. So first condition is anti-symmetry. If I've given 3 values, if I say that the first value, V, is less than or equal to W, and W is less than or equal to V, then I can safely say that V is equal to W. This is the anti-symmetry property. Then we have transitivity. If both V is less than W and W is less than X, then I can say that V is less than or equal to X. Totality, that's the third property. So either V is less than or equal to W, or W is less than or equal to V, or both. Okay, so some examples of the total order is the standard order for natural and real numbers. So if you look at your integers, they go from 1, 2, 3, 4, up to infinity. Chronological date order for the dates and times. So January comes before February. March goes after February. Alphabetical order for strings. For example, A goes before B. Or a string, Ahmed goes before Saleh, because Saleh is starting with an S. All right. Okay. Here's another example. Okay, transitivity property and totality property. If you look at the courses that we have in the university, so to take this course, you would have finished taking CS102. Before that, you should have finished CS101. So all these 3 courses are linked together. They are prerequisite for one another. Okay, so this is defining the order. But would it be possible, or should I say this way, that it would be wrong to take CS101 after you finish CS210? Okay. So when I'm writing a program or code for a sorting method, okay, the goal is that I should be able to sort anything and everything within the data set given to me. So, example, the sort method defined in Java is available in the java.io.file and util methods libraries. Okay, so if I provide a double as a data set, okay, would it be able to sort a string, or the other way around? For example, if I provide a string data set, would it be able to sort it using double? Okay, so we have to be careful about this. Which defines the key? What kind of data type of key is there for the item or the data set? So it's important to define the comparative method. Okay, how are we going to compare the data types? First of all, it has to be the same data type when we're comparing it. If not, then you have to define some kind of mechanism, okay, so that the different data types can be compared. Okay, so here are some examples. So if I'm comparing two strings, I should be able to return 0, 1, or -1. What it means is, if I return 0, this means both of the strings are identical. If I return -1, this means the first string is smaller, or it comes before the second string. If it is +1, this means the second string is smaller or goes before the first string.
Doctor, can you repeat that, please? I didn't get it.
Okay, it's going to be clear with this slide. So my comparable interface or comparator, I have to define two values. So think of it like this, a method, a comparative method. which takes two parameters, V and W. If both of them are equal, my comparator is going to return 0. If the first one is less than the second one, my comparator will return -1. If the first one is larger than the second one, my comparator is going to return +1. Okay? So this is the basis. And the comparator method is only going to return 3 possible values. It's either -1 or 0 or +1. So if you're writing a program where you have to compare different kinds of data sets, then you have to define your comparator method in this way, that it returns these 3 values. Okay. When this is clear, let's look at another example, which could be slightly different from what we just said. This is the date class. Date, as you already know, that it goes with days, months, and years. So what you see in front of you is code for the compare to method for the date class. So here what's happening is the date method, okay, it's taking month, day, and year in that order. So if I provide it with 2 dates and ask the method which one goes first, which one goes later, or simply the first date comes before the second or not. So what we can do is we can start comparing the underlying data set, which is the months, day, and year. So first what we can do is we can compare the year. Okay, if the year for the first date is less than or is before the second, we return -1. If it is more than the first one, this means it goes later. In other words, it's bigger, so +1. If both of the years are exactly the same, we go into the third if condition, then we start comparing the month. So the month comes before the second month, we return -1. Else we return +1. Now, if the year is the same and the month is the same, now we need to go and compare the day. So we check the day. The first day is less than the second day, return -1. If it is larger, we return +1. But if none of these was true, this means that you have the exact same day. So we're going to return 0. Okay. So having clarified these details, okay, let's have a look at our next sorting algorithm, which is selection sort. Let's see how this works. So I'm going to show you a simulation. Have a look at it carefully. Think about the algorithm, how are we going to implement that, and then we're going to have a look at the code for this. Imagine I have this set of cards. All of them belong to the same house, and we would like to sort them in ascending order, which means the smallest comes before the largest goes at the end. Okay, so let's say this is the initial positioning of the cards. Now, pay attention and be very careful about this. Selection sort, we're going to define 2 indexes. We're going to have I, and we're going to use the one to move around. The goal is to find the smallest. The goal is to find the smallest value and bring it to the left. So we start with I, okay, and now we're going to go and compare I with all the possible values. So 7 is smaller than 10. 7 is smaller than 5. No. Okay, so we're going to define 5 to be the minimum. We're looking for the smallest. Now we compare 5 with 3. 3 becomes the smallest. 3 becomes minimum. 3 compares to 8. That's wrong. 3 compares to 4. Okay, that's wrong. 3 compares to 2. So 2 becomes the minimum. Now 2 compares to 9. Okay, it's wrong. 2 compares to 6. That's also wrong. So what happened is, to look for a minimum, you have to go through the entire data set. Okay, so we had to check all the different cards available to you. Once you find the smallest one, we're going to replace that with the current position.
So, Doctor, the runtime would be like between big O of n and something else?
But no, it's still going to be of n squared.
Oh, okay.
Yeah, we're going to see this now. So keep paying attention, Yani. This is what's happening. So this was the first iteration. Now the second iteration. We already know that the value that we have put on the leftmost is already the smallest. This is the correct position for 2. Okay, so now we go for the second iteration. Again, we'll repeat the same thing. We have to find the smallest. To find the smallest, I have to compare 10 with 5. 5 is smaller. 5 with 3. 3 is smaller. 3 with 8. 3 is smaller. 3 with 4. 3 is smaller. 3 with 7. 3 is smaller. 3 with 9. 3 is smaller. 3 with 6. 3 is smaller. Okay, so once I've gone through all of it, I realized 3 was the smallest one. 3 is the minimum one. So I'm going to swap position I with the position minimum. Okay, this was my second iteration. Now I know that the leftmost 2 cards are already sorted. Okay, again, repeat the whole process again. So this time the minimum was 4. So we're going to swap 4 with 5. Okay. So now we have 3 items in order. Next, I find the minimum. The next minimum would be
5.
5. Remember, to find the minimum, you have to go through the rest of the cards, all the cards.
Oh, so we have to do it n times?
Yeah.
And then, so
So
n
you
times.
have to do it n times, and overall number of iterations is also n. But this is going to work better. It's going to be faster than bubble sort.
Why is that?
Okay. Notice your data set is becoming smaller and smaller and smaller. In every iteration, it decreases by 1. So now the size is 3. Now the size is 2. Okay? So your inside loop basically is running n minus 1 times in every iteration. So this is what happens.
Doctor, for the comparison, it should be like n plus n minus 1 plus n minus 2 and so on until until it's 0 and minus n, which is 0.
Very good. Yes, that's the idea. So let's have a look at this now. So selection sort. Okay, so I'm going to give you another simple example, and let's see how this is going to work out. So here's my original data. Okay, this is my original data. Okay, and we would like to sort it. So let me define I and minimum. Okay, so I is the position. That's my first iteration. Okay, first iteration. So first iteration, let's go with 0. This is position 0, 1, 2, 3, and 4. Let's put this in the array. Okay, now to find the minimum, which is at 1. Okay, so we're going to swap it. So 1 swaps with 3. The rest of the data stays as is. Okay, so here notice how many swaps did you make and how many comparisons did you make. Okay, so how many compare to find minimum? How many times you had to compare? You compare this with this, then this with this. That's 2. This was the smallest now. This with this. This with this. Okay, so there was 4 comparisons and 1 swap. Okay, next we know that this part is already sorted. Okay, we have to work with this one. So now I is at 1, position 1. Again, we find the minimum. We'll find the minimum. So we check this is not the smallest. Compare this with this. No, this becomes smaller. This with this. 3 is still smaller. 3 with 2.
So we compared 3 times.
So we're gonna compare 3. Okay, minimum position is 4 now. So we compared 3 times.
And 2 swaps.
Swap.
2
With
swaps.
With 5. Okay, so we're gonna have 2 here, and this becomes 5. So far so good. So we know that this much is already
Yes.
done. Okay, let me put it this way. So this is already done. Now we have to take care of these. Like next iteration, I is 2. Again, find the minimum. 3 happens to be the minimum. But still, to find the minimum, we have to go and check with this one and check with this one. We have to make sure that we have to browse through the entire data set before you can say that this is the minimum. So now this is the minimum. No need to swap. Okay, so comparisons is 2 and swaps is 0 this time. No need to swap. Okay, so now we have 1, 2, and 3. Okay, what is left is 6 and 5. Okay, so sorry, this was 2. All right, next iteration, position 3. Find the minimum. So of course we're going to compare it with this one, and then we realize that that is a minimum one. So number of comparisons is 1, and now we have to swap it. So swap 5 with 6. So we're going to have 1, 2, 3, 5, and 6 is left out. Okay, there is 1 swap. So far so good. Now the last iteration, of course, there's only 1 element left. So you can skip here, you can stop here, or you can continue. Okay, in this case, that will be the current position. And now you have 1, 2, 3, 5, and 6. Now your data is sorted.
Doctor,
yes.
for the second one, isn't the swaps 2 instead of 1 for the second time, where the loop are 3?
You want this one?
Yes.
Yeah, so we're looking for the smallest element now. So it was, 5 compares with 3, 3 compares with 6, 3 compares with 2, 2 was the smallest. So 3 comparisons.
And 2 swaps, because we swapped 3, 5 with 3, then 3 with 2.
No. We find the smallest one, and only that one gets swapped with the first one. So here, what we did was we found the smallest, which was 2, and we swapped 2 with 5. Only 1 swap.
Okay, clear now. Thank you.
Here, the smallest is 3. No need to swap. Here, the smallest is 5, so we need to do 1 swap. So in every iteration, okay, in each iteration, we're doing 1 swap. Okay, worst case, 1 swap in every iteration. Okay, how many comparisons are we doing? That depends on the data. But what if your data was like this? Okay, what if this was your data?
It is decreasing, so it's like it starts with this number, then decreases to 1.
Yeah, well, imagine we have to sort this in ascending order, and it should go like 2, 3, 4, 5, 6.
So it will be like here is 5.
So first time it's gonna be 4,
4
and
swaps.
then 3, and then 2, and then 1.
1, and then maybe 1.
Okay, yeah, or you can completely skip this step. So here we're talking about n minus 1, okay, and then n minus 2, and then n minus 3 up to plus 1. Okay, so this is the number of comparisons that we're making. Remember this series? Does that look familiar?
Recursive method?
Yes, this is a series.
This is your series. We used to give it by this formula.
This one, yes.
Okay, so we have already studied this thing. This is like O of n squared.
Yes.
Okay, so the worst case scenario for selection sort is if your data is pre-sorted in the other order. So if I'm trying to sort this in ascending order, but the data is already sorted in descending order, that's the worst case scenario for selection sort. Okay, so here number of comparisons is going to be O of n squared, and number of swaps is going to be n, worst case scenario, okay? O of n. Because in every iteration we have to do at most 1 swap. At most 1 swap. In every iteration, we have to do at most 1 swap. It could be less than that, but because we're looking at the big O notation, so it's going to give me big O of n. So remember this, selection sort, swaps is O of n, and comparisons is O of n squared.
Dr. Swab's if the selection or the list is fully sorted already, then my swabs will be 0.
Very good question. Okay, so what you're saying is, what if your data looks like this? 2, 3, 4, 5, 6. Okay, so every time you still have to go and compare each one of them to find the minimum. So the number of comparison would still be big O of n squared. But now number of swaps. Okay, how many swaps?
We'll have 0 swabs, Dr.
Okay, this is the best case. So swaps is 0. Okay, or can we say constant? And comparisons is still big O of n squared. Okay, so that's the best case scenario for selection sort. If the data is pre-sorted in the same order that you want it, still is going to take O of n squared time. Okay, but the number of swaps would be constant or 0. Okay, is this clear? Any questions so far?
Thank you very much, Dr.
Doctor, it's big O of n squared because it still searches the whole thing.
Good point. That's why overall it's still big O of n squared.
Okay.
Remember, we always look at the worst case scenario. Okay, so if this is clear, let's have a look at the code. Okay, I just already explained all of this. Okay, so here's a code. So according to the code given in the book, it's defining the less method, which simply compares two values. Okay, we already talked about this before. And then there's exchange method, which is swapping. So again, we already talked about this. Okay, and let's have a look at your entire code. This is the code for selection sort. So if you look at it carefully, let's see, in the beginning, we're going to have integer n equals a dot length. So that determines the size of the array. So the outside loop runs n times, exactly n times, because we have to go over each and every item in the array. And now to find the minimum, we're defining integer min equals I, and then we have a loop. The loop is never starting from 0. It's starting from I plus 1. Okay, I plus 1. And j is less than or equal to n. So you can see this thing, the second loop is connected to the first loop. So directly, just looking at the code, you can say this is going to give you the series, and the runtime would be big O of n squared. And the rest of the code is what we just saw before. So if we compare the first value with the second value, okay, and the second value happens to be the minimum one, so we're going to update the minimum value if it is true, of course. If not, then we do not change the min. So the inside loop is going to take up to n times, and outside loop it always takes n time. So overall, the runtime would still be big O of n squared. But now the question is this going to be faster than bubble sort?
Faster than bubble sort?
Bubble sort.
I don't think so. Maybe it is, but it's not that big of a difference.
So if you see, this was bubble sort. Okay, we went over this. The number of comparisons was O of n squared, and number of swaps was also O of n squared. Okay, so if I compare a bubble sort with selection sort, the number of comparisons is still the same, but bubble sort does more swaps compared to selection sort. Okay, at most, selection sort is going to do O of n swaps. Bubble sort, worst case scenario, is O of n squared. Okay, so I can say that the selection sort will work faster compared to the bubble sort. There's another thing that you can see. Bubble sort does exactly O of n squared number of comparisons. Exactly O of n squared number of comparisons. Here, we're not doing exactly O of n squared number of comparisons. It's kind of looking like this. So if you want to give a mathematical equation for this, it's going to be n over 2. To be exact, n into n over 2. That would be the number of comparisons.
So it would be n squared over 2?
N squared over 2. Yeah, you can say that, yes. Or, to be more precise, the series. So compare this with that, then of course this one is going to be at least half as fast as bubble sort. Okay, let's have a look at a simulation for this. So some 20 random values. We'd like to sort them using selection sort. See how this works. We find the smallest and bring that to the left side. Did you notice that as we reached the end, it became faster? Let me run it again. Notice that it's getting faster. Can somebody tell me why is it getting faster? Anybody? Nobody's responding. What's going on? Should we take another attendance or what?
No, with you, but I think I don't know. I don't know.
Here, doctor.
So now why is it getting faster?
Because of the number of searching less.
Good.
The-
The data set, the sample space is becoming smaller. Okay, it appears to get faster. All right. What if we have a data that looks like this? It's almost pre-sorted, partially sorted. Okay, would it work faster or not?
I think the swaps would be less, but the comparison would be same.
Good point. So number of swaps would be the same. Number of swaps could be less, but the number of comparisons would be the same. So there's no difference.
Yes.
Okay. Now in the exam, if I ask you to simulate this for me, show me how this works. So you would have to do something like this. You have to show me step by step in every iteration which thing gets swapped and which one is the smallest one. Okay, you have to show all the iterations for that. Okay, let's have a look at the third and the last algorithm for today. This is insertion sort. So let's first have a look at the simulation, and we'll notice that this is different compared to what we just saw. So far what we have studied is the first one was bubble sort, the second one was selection sort, here is the insertion sort. So imagine this is the data given to you. Now this is how it's going to work. So we're going to define I, first position, and we're going to define J. In the beginning, that's also going to be equal to I. Now what we do is we pick one card from the right side, and then we sort these. Okay? So 7 comes before 10. This means we don't have to swap it. Okay, next iteration. We go pick the next card. Okay, both I and J go to position card 5. Now what we do is we're going to compare 5 with 10. So 5 is smaller than 10, we're going to swap it. 5 is smaller than 7, we're going to swap it. Notice what's happening. Okay, let's go to the next iteration. Things will become more clear. Again, I and J go to card number 3. Now we move leftwards, compare 3 with 10. So we swap it. Oops. Compare 3 with 7, swap it. 3 with 5, swap it. Okay? So how many swaps were there?
3.
3 swaps. Okay,
Yes.
good. Next, now we have 5 cards. Again, repeat the whole process. 8 is less than 10, swap it. 8 is less than 7, no, stop. Okay? Next iteration. INJ go to card number 4. Again, 4 is less than 10, swap it. 4 is less than 8, swap it. Less than 7, swap. Less than 5, swap.
And then we did
3,
4
no,
swaps.
stop. Okay? Go with 2. So 2 swaps with 10, swaps with 8,
Until the ending.
swaps with 7, 5, 4, 3, goes all the way to the end. Okay? Next is 9. 9 swaps with 10. 9 is not smaller than 8, so we stop. Okay? So, can you tell me what's going on? In every iteration, how many comparisons are we making?
We're kind of doing comparison for each one.
Like, one thing is clear, we're not making n comparisons, okay? It's less than n.
Yeah, it's less than n. Okay, but then no,
Okay?
it's still like near n. It's like
Yeah, this is the
Is
trick.
it log of n, Doctor?
No, it's not log. No way. Okay? So,
It's
what
below,
about swap?
as my colleague said, it's below n, not n, but it's below. But maybe it's between log of n and n.
No, we cannot say log of n. Log of n doesn't work here. So it's n or something close to n. Okay, look at the last one. So again, we swap, 1 swap, 2 swap, 3 swap, 4 swap, and we stop. So we're not even doing n number of swaps, and we're not even doing n number of comparisons. So we have something between n and n squared.
yeah, we're not kind of sure because it could be n over 2. It could be n. It depends.
So simple answer is it depends on the order of the data. Okay. Now let me show you some examples. Let's work out with a few examples and let's see how this works. So this is insertion sort. Okay, I'm gonna go with the small data set. Let's go with 5 items. Okay. So first iteration. First iteration, what's going to happen? So we go with this one. This is your INJ. Okay, obviously this is sorted. So next one is INJ. Going to compare 5 with 2. So it's not smaller. So 2, 5. It's not smaller. So
And then we insert 4.
So remember, number of comparisons and number of swaps. How many did you compare?
1.
2 values. Compare this with this one.
These are 2 comparisons or the 1?
No, one comparison. The number of swaps, nothing. Yeah.
Yes.
Okay. So this goes as is. Next, we're gonna pick this one, 4. So 4 comes over here, and then we stop, right?
Yes.
So how many comparisons do we make?
2 comparisons and 1 swap.
And 1 swap. So now we have 2, 4, 5, 3, 1. So this much is done. Okay, next is we go with 3. So 3 compares with 5, we swap it. 3 compares with 4, we swap it. 3 compares with 2, we do not swap it. So how many swaps, how many comparisons?
4? Or 3? 3. Yes.
3 comparisons and 2 swaps.
Yep. Oh, it's actually going like in a.
Okay, yeah, let's try 1 now. Okay, so 1 comparison, 2 comparisons,
4 comparisons.
4. So it's exactly 4 comparisons and 4 swaps.
Yes.
Okay, now
Is this the worst case scenario or no?
so
No, that's not.
No, it's not the worst case scenario, but in this particular case, it's giving me O of n. O of n. لا, You have to add them up, right? So what's the total?
4 and 4, 8, and then 10 for the first one.
Basically n minus 1, this is n minus 2, n minus 3, n minus 4. Isn't it giving me of n squared? Again, series. Remember series?
Yes. Okay.
And swaps, kind of similar? Kind of?
Not in an orderly manner, يعني.
Yeah, kind of. So we can say it's something close to O of n squared. O of n squared. Okay? So compare this with what we studied before. This one was giving me almost always up to O of n swaps and n squared comparisons. But here, this is giving me O of n squared comparisons and O of n squared swaps. So which one wins?
The first one? Obviously.
Selection. Selection appears to be faster than this one. But
Yes.
what if the data looks like this? What if this is your data?
This is already ordered.
Yeah, it's already ordered.
So basically, the comparisons would be 0.
Comparisons would be, so we're going to compare 1 with 2. Yeah, 1 is already smaller. Okay, so 1 comparison, 0 swaps. Okay, next we're going to pick
2
1,
and 3.
2, and 3. So again, 1 comparison, we compare 3 with 2 and we stop. Then we first
And
swap.
then 0. Okay.
Okay, and then we pick 1, 2, 3, and 4. Compare 4 with 3. So this 1 comparison and 0 swap. And the last one, same thing.
So
what
basically
happened now?
constant.
This is constant, and this is
Big
n.
O of n, yes.
Add it up. So n. See that? So if the data is pre-sorted, if it is sorted already, pre-sorted, it's giving you O of n time. Isn't this really fast?
Yeah, only in this specific
So
situation.
this is the best case.
Okay.
Okay, this is the best case. It's giving you O of n time. But this is much better than selection and bubble sort. Okay?
Just in that case.
Just in this case, if the data is pre-sorted or almost pre-sorted. Hey, what's the worst case scenario? Let's look at the worst case for insertion sort.
Descending order.
Yeah, insertion sort, worst case. So imagine you have data like this, and we have 5, 4, 3, 2, and 1. They have comparisons and swaps. So this compares with this one.
Yes.
First iteration, so it's going to swap.
So
Okay.
one
One comparison, one swap. Okay. Next, we have 3. So 2 comparisons. This compares with this, and then this compares with this. 2 comparisons and 2 swaps.
Yes.
Okay. And then we have 2. So again, 3 comparisons, 3 swaps. 2 compares with 5, then 4, then 3.
So it's big O of n squared 2
Okay.
times. So
And then we have
2 bigger
2,
than
3, 4, and 5. And then we compare with 1. So we have 4 and 4.
yeah, basically
So this is the
2
worst
n squared.
scenario. So this is exactly series. Okay, it's series. So
Yeah.
remember the series, it's going like this. So we have 1, then we have 2, we have 3, then we have 4. So it's like this. Okay, if you want to be precise, it's going to give us O of n squared over 2, both of them. So bottom line, it's still faster. It's still faster than bubble sort. Sorry, than bubble sort. Bubble sort is always giving you exactly O of n squared. Okay, so it's more faster than that. But here, this probably wins because here the runtime would be O of n squared over 2, and this would be O of n.
Unless it's pre-sorted.
Unless it's pre-sorted. So if you already know that the data is almost already pre-sorted, we'd like to go with insertion sort. If it is not, then it seems insertion sort and selection sort work the same. Let's look at how we implement this.
Doctor, insertion sort in the descending order. Is it big O of n squared? Because it's big O of n squared over 2 for 2 times.
Sorry, come again. What were you saying?
The insertion sort, is it big O of n squared exactly? That in descending order?
In descending order, not exactly. It will be n squared over 2. But again, it's big O of n squared, yes.
Okay.
Okay, so we already looked at the algorithm. Here's a code for insertion sort. So we have 2 loops. Again, just like before, the first loop is going from 0 to n. And the second loop is connected to the first loop. So again, you can see that the series is there. And then we're comparing the value of a of j with the one before it, which is a of j minus 1. So if it is smaller, we exchange it. Okay, else we break. So it's very simple. Let's look at the simulation for this. So this is more data. Okay, we put more data over here so you can really see the difference. These are some random values if I run it. So you can see that if a smaller value comes towards the right side, your algorithm becomes slower. Okay, so here the runtime is O of n squared. But if your data looks like this, okay, what happens? Remember,
It becomes big O of n.
This is the worst case scenario.
Okay, yes.
This is the worst case scenario for insertion sort. Everything ordered in the opposite direction. So you'll notice it gets slower and slower and slower because it has to do more number of swaps. Okay. Anyways, and this was something close to the best case scenario. Here we have to do less number of swaps because your data is almost pre-sorted. There you go. Very quick.
Oof, yeah, it's much faster than the selection sort.
Yes. So now you can see this. If the data is pre-sorted, okay, insertion sort works in O of n time, which is much faster than the earlier 2 algorithms that we saw, the selection sort and the bubble sort.